going to talk about geometric methods for the approximation of high-dimensional dynamical systems.
Thank you for the introduction, Simone, and thank you for the invitation. I'm really happy to be here. I would like to talk about data sets that arise from simulation of high-dimensional dynamical systems, especially stochastic dynamical systems, and a bit of molecular dynamics in particular. And I wanted to start with a sort of list of issues that arise from analyzing high-dimensional dynamical systems and what it means to do dimension reduction for dynamical systems. It doesn't mean just reducing the dimension, but you would like to reduce the dimension, but also have a dynamical system in the reduced dimension that is somehow close to the original one. And so this is motivated by the fact that many dynamical systems of interest in applications coming from physics are characterized by a very large number of ordinary differential equations or stochastic differential equations. And when you have many, many, many of them for many degrees of freedom of the system, you might have the equations, but you can't solve them. And it's very hard to determine even qualitative properties of the dynamics. And so the question behind model reduction is that of having an original system, which I'm gonna call the states at time t of the system by x sub t. And again, typically they're going to be stochastic. And the states of the system live in that script S, a high-dimensional state space. Think of that as R capital D, where capital D is the large dimension. And you have trajectories in that space, those wiggly curves over there. And one goal of model reduction is the following. You would like to construct a map phi that takes the high-dimensional state space script S into a lower dimensional one, a tilde script S, with only small d dimensions instead of big D dimensions. And it maps trajectories from the high-dimensional space to a lower dimensional space. And there are going to be equations in now small d dimensions that generate these usually stochastic trajectories x tilde t. And you would like to do this in such a way that, maybe you have an approximate inverse that allows you to, take an initial condition in the high-dimensional space, go to the low-dimensional space or low-dimensional representation, run your path, and in a certain sense go back and be able to promise that you're back to where you would have been if you're simulated in the high-dimensional space to start with. And of course, that's going to be impossible in most cases. And we're going to make a lot of assumptions to try to come up with a setting where some things are possible. And I wanted to make you aware of several obstructions that there are to this plan. So the first one is, of course, that the original state space is very high-dimensional. And as we are well aware, in high dimensions, many estimation tests and many statistical estimation tests go wrong. If you take the task of simply estimating a function f, maybe you know the process as an unknown drift coefficient, like in some of the presentations before, and you want to estimate it. Well, if that's high-dimensional, even if it's smooth, say it's Lipschitz 1, the number of samples that you need to see in order to estimate just a drift will scale exponentially in the dimension of the space. And our capital D is going to be easily in the hundreds of thousands, tens of thousands, so we can't have even 2 to the 100, right? So how are we going to try to bypass these effects, this negative effect dimensionality, sometimes called curse of dimensionality? We're going to make the following assumption. We're going to assume that the trajectories of our dynamical systems are close to a low-dimensional set, something like a manifold, or maybe something more general than a manifold. So while the trajectories live in very high-dimensional space, they are in fact concentrated on an unknown low-dimensional manifold. It could be an attractor, it could be an inertial manifold, and so on. That's the assumption that we're going to use in order to bypass the effect of the course of dimensionality. So the blue thing over there represents sort of a low-dimensional set near which the trajectories concentrate. The dynamics of many of the systems of interest are extremely complicated. And if you have a system which is hyperbolic or highly sensitive to perturbations in inertial conditions, Those are hard to simulate even in low dimensions. If you construct a simulator and that starts making error epsilons, and those errors exponentiate in time, becomes exponentially large in time, of course, there is no hope to have any large time accuracy, and we will care a lot about large time accuracy in this talk. Then, what we would like to do is going to fail. So the way we're going to go around this problem is the following. First of all, we will consider dissipative systems, diffusion-like systems. There is going to be noise injected in these systems, so we definitely don't want any sensitivity to initial conditions. And the kind of quantities of the system that we're going to be interested in preserving are not going to be exact positions, exact states of the system, but functionals of states, which are something like large time averages or large space averages. And so these averages will not care about the details of the state itself. And again, I'm going to make all of this precise, but these are some of the abstractions that we encounter. Another phenomenon which occurs in a lot of systems of interest is the so-called phenomenon of metastability, which is a phenomenon where the system is stuck for very large time in certain region of space, and then there are rare events that take the system to a different set of states. So you could consider a simple first-order stochastic differential equation in that form, where at every time t, you get a random kick from Barnum motion, that's a dBt, and then you have the drift coefficient, which is in the form of the gradient of the potential. This is just in 2D, and these are the level sets of the potential energy. And so blue corresponds to low energy, and so the system, say, starts over here, the gradient of u is trying to keep it towards the center of this first metastable state. The random kicks might push the system out, but the gradient keeps pushing the system down. But then eventually a very unlikely sequence of kicks is going to take the system, make it climb the energy, and then the system is going to fall into state 2. And so this is a time trajectory. The horizontal axis is t, the vertical are the coordinates of the point, the two coordinates, blue for the first coordinate, red for the second coordinate. So at the beginning, those coordinates are very close to 0, so we are over here for a very large time, till all of a sudden the blue coordinate, the first one, switches to the value 1.5, and so this jump over here corresponds to a trajectory that goes to cluster 2. It stays there, it tries to escape, it fails, and then eventually it escapes, and then it goes to another cluster, and so on. But this time axis is, it's a huge number of time steps. And so the metastability is an abstraction because you need, if you start in 1, you're going to be stuck in 1 for a very, very large time before you see the other regions of space. And so you need to compute a lot in order to just get a picture of how the state space looks like. And, and the way we're going to go around this is that we're going to start with our simulator for the original system. We're going to construct a simulator which is much faster than the original one. And so even, if we had to run a very large number of time steps for the original system, and that was expensive, we're going to construct a new simulator which is going to be faster in terms of real-time computation, in terms of time that it takes to run in the real world, and it's going to still require for us to do a very large number of steps, but those steps are going to be computed in a much faster time. And finally, another unrelated abstraction is roughness. So many potentials that arise in applications are not nice and smooth like the one that I pictured before, but they're full of ripples. And this happens a lot in the state space of molecules, for example. And the landscapes are very, very rough. And so if you need to run a simulation in a landscape like that, or just in 1D, if we want to just extract the simplest example where this arises, you take a one-dimensional system of the same form as before. This is the potential, and it looks smooth, plus high-frequency perturbations. And if you need to run a numerical simulation for this, since the gradient of u is very, very large, because of these high-frequency ripples, then you will need to take time steps which are really, really short. And so it would take you a very, very large number of steps in order to explore the state space. And the way we are going to try to get around this is going to be the following. Since we're going to be interested in functionals which are large time averages of the system. You know, if you look at the system for a very large time, the behavior of the system is essentially you're in 1, with some probability you stay in 1, with some probability you jump near 0, with some probability then you jump back to 1. And so the system at large time has a behavior which is highly compressible. And of course, the ripples do affect the time that it usually takes to go between 0 and 1 and conversely, but that we should be able to compress that out. We should be able to homogenize the system into a much simpler system with either a smooth potential or perhaps just even 2 states in such a way that we do take into account the effect of the ripples. The examples that I'm going to discuss for part of the talk come from molecular dynamics, albeit some things are more generally applicable. And I wanted to talk about 2 separate problems, time permitting. The first one is a problem of designing coordinates for reducing the system, given enough data, enough simulations about the system. And the second part is going to be about how to quickly construct these reduced models without having access to very long trajectories of the system. So in the first problem is the following. So you have a dynamical system for which you have a numerical simulator. The state space is very high dimensional. The simulator, every time step of the simulator is expensive. And maybe what is being simulated is a molecule. So when you simulate a molecule has m atoms, and so 3 m coordinates. And if you go in phase space, you have 6 m coordinates. And your numerical simulator is outputting at every time step the positions of all these atoms. The dimension of the state space can be very large because the number of atoms is in the, for small molecules is in the dozens, for large molecules is in the millions. So the state space can be very, very high dimensional. And people are very interested in simulating these molecules for a variety of applications and in understanding the result of those simulations. And what is often done is the following. So you call in a domain expert who looks at the molecule and says, well, these molecules has 2 degrees of freedom which are really crucial. For example, those 2 dihedral angles, phi MC. And he will say, okay, those are good effective coordinates for the system or reaction coordinates for the system. Consider those 2 coordinates, go in the plane spanned by those 2 coordinates. Those are in fact angles, so this is actually a torus. And let's draw an energy, a free energy surface, as a function of these 2 variables. What does that mean? Well, you fix a value of those 2 variables, phi MC, for example, minus 50 and 0. I'm electrically charged. So minus 50 and 0. And if you saw many molecular configurations during a lower run of molecular dynamics that have approximately those values of phi MC, then you say that that state has a low free energy and you color it blue. If you go to a state around here, it's yellow, meaning that free energy is very high, meaning that during your long simulation you saw very few molecules which were in this region. And so essentially this is a histogram. So this is so phi MC for if you fix phi MC, you're determining a submanifold of a state space, and you're essentially binning your states based on this foliation of the state space. And so if you get a picture like this seems very pleasant because there are 2 blue lakes, 2 regions of low effective energy, where the molecule is going to be trapped for a long time. So those are 2 metastable states. And then every now and then the molecule is here, is being kicked around by noise, and then it climbs this mountain pass over here and is going to fall in the other metastable states. Remember, this is a torus, so this part over here is connected to the part over there. And so if that is true and accurate also numerically, then this is a very nice representation of the system, and it's just a 2-dimensional representation. The system there is about 30 dimensional, so you go from 30 dimensions to just 2. And a nice story to tell about what the metastable states are. So what we would like to do is sort of replace the manual step that requires an expert to come in and make suggestions about the useful degrees of freedom of the system. So we would like to have a machine learning algorithm that is given long trajectories of the system in the high dimensional space, it looks at the configurations during those runs, and it outputs sets of coordinates which should be good for at least the large time dynamics of the system. So we've done a lot of work here. So again, here we allow ourselves to collect long trajectories, and then we want to output the reduced model. And so we've been doing a lot of work in the past several years with people in chemistry, in particular with Cecilia Clementi and their group in the chemistry department at Rice. I'm going to simplify and consider the simplest model possible, which is very realistic for molecular dynamics. So it's an equation in the same form as the one that we already met. So here x is a vector with 3 m coordinates of the m atoms in the molecule. And its velocity as a deterministic component minus the gradient of u, where u is a potential that takes into account all the forces between the atoms. And a stochastic component, a w dot, which is Brownian motion. Typically it's colored. Here the covariance of the noise, the diffusion coefficient is just a multiple of the identity. And where is the noise coming from? Well, the molecules are usually embedded in, say, water or in some solvent, which has a huge number of atoms that you would like to not have to simulate. And so you could say, well, those atoms move very fast. They kick the molecule of interest. And this sequence of really fast kicks is random noise. And so the noise term sort of incorporates the effect of the molecule being inside solvent. All right. So we're interested in systems like that. We allow ourselves to collect a large number of states for that system, and we would like to perform dimension reduction. Now, already in earlier talks, the basic method of performing dimension reduction, which is principal components, has been mentioned. And I wanted to show a simple example where principal components fails. The idea here is that the trajectories of these molecules might be intrinsically low dimensional in the state space, but a linear dimension reduction technique like principal component analysis, which just projects onto a low dimensional plane, is not going to be sufficient. And to me, one of the simplest examples where PCA, I don't think, does a good job is the following. So I have a data set which is just made of black and white pictures of white circles on a black background. Each of these pictures has about 4,000 pixels, it's 64 by 64. And here are some of my data points. So the radius of a circle is fixed, so the only thing that is varying is the center of the circle. And this is a data set in 4,000 dimensions, and you can do principal components. And the principal components sorted from the first, from the first to the sixth down here are essentially Fourier modes in 2D, because the data set is translation invariant. And so if you want to find the eigenvectors, what's going to diagonalize translations, you're going to get Fourier. And you can ask whether the data set is well approximated by a low-dimensional plane. So by using PCA, so you can, as a function of the index I, you can plot the singular values in logarithmic scale. And the singular values decrease, but now they decrease pretty slowly. So if you ask, is there a plane that approximates my data with relative, with about 1.5 digits of accuracy, this plot will tell you that you will need at least about, 800 or 1,000 dimensions. So you're in 4,000 dimensions, and what this is saying is that there is no plane with less than 1,000 dimensions, such that the error that you incur in the mean square sense when you project the points onto the plane is of the order of, half a digit of accuracy. And so this data set is very far from being close to a low-dimensional plane. And that is also obvious because we're just doing Fourier analysis. So projecting onto the principal component is just doing the Fourier analysis of those data points, and those data points are discontinuous functions. So the Fourier coefficients decay very slowly. But what is the point? The point is that this data set actually is a very nice two-dimensional manifold in 4,000 dimensions, because here is a parametrization. If I give you the coordinates of the center of the circle, you know how to produce 4,000 numbers that represent that image with the circle at that position. So this is a global parameterization of the manifold from the unit square to the manifold. And so this is a two-dimensional manifold, and yet it's very far from being close to any low-dimensional plane. So PCA can be deceiving, but not all is lost, of course. one can use PCA to actually, for example, estimate what the intrinsic dimension of the data is, right? So how can we decide, if given simulations of a molecule, how can we decide that the trajectories lie close to both trajectories lie close to a low-dimensional manifold? Or how could we decide that this data set was in fact intrinsically 2D? PCA is not telling us that. So I wanted to just present one slide on how to do that. This also came up in Simon's talk this morning. This is joint work with Anna Little and Lorenzo Rosasco, appeared in ACHA maybe a year ago. So what we do is the following. So the question here is, you're given a bunch of points which are close to a low-dimensional set. That's the green set M, maybe a low-dimensional manifold. And what you see are actually not the points exactly lying on the manifold, but those points perturbed by noise. So instead of being exactly on M, those points are going to be mostly in a tube around M. That's what I represent with those two things around M, M plus eta. So you get noisy points where the original points are on a manifold and are perturbed by high-dimensional noise. Can you decide, given those points, if there was an underlying low-dimensional structure? And the way we do this is we use principal components, but not global principal components. We use multi-scale principal components. So we pick a point Z, we pick a radius R, and we do principal components, and we store the singular values. And then we change R. And when R is, what's going to happen is the following. So when R is really small, well, you pick a point, you pick a very small ball around that point, well, you may have no points in that small ball because you have a finite number of points, first of all. And secondly, points have been perturbed by high-dimensional noise. High-dimensional noise is going to push the points far from your manifold. And so when R is small, you're going to get no information by doing principal components in a small ball around Z. As the radius increases, though, you will start getting more points. But when you get more points, many of those points will have been affected a lot by the noise, by the high-dimensional noise. And what you will be measuring with PCA is simply the size and the shape of that noise. But then when the radius grows even bigger, it goes above a certain characteristic scale of the noise, you will be able to see that a certain number of singular values in the principal components of the points in that bar is going to grow with the radius. Those are principal values that correspond to principal directions, which are essentially tangent to the underlying manifold, while all the other singular values are going to be stuck at measuring the size of the noise. And so if you run this, so the point of this procedure is that you do principal component analysis at all possible scales around each point. And here is an example where, as a function of the radius R, I plot the singular values of the data. The data set is the data set of those images. I plot the singular values of the data in a ball of radius R around a fixed point. And what you see is that there are two singular values that grow linearly. Those correspond to the fact that this data set was intrinsically two-dimensional. And then all the other singular values grow quadratically. They're measuring certain curvature. In fact, there are certain functionals of the sectional curvatures that Simon talked about this morning. And from this, we would deduce that the data set is intrinsically two-dimensional, and we should look at this data set in this range of R's, because when R is too big, then the data set is curving too much, and it's not clearly two-dimensional anymore. And in fact, we know that if we take R very large, we're not going to see anything. Because we will be doing global principal components. All right, so this was a small excursus on how to estimate intrinsic dimension, and we are going to use this in 5 minutes or so inside the model reduction. So let me go back to our SDEs for molecular dynamics. So those SDEs are very high dimensional. U is a highly nonlinear function. The trajectories are, nonlinear in every way that you can imagine. So it is convenient to switch from the point of view of the SDE to a point of view of PDEs. So you can write a PDE in the unknown P, X, Y, T, which is the density of probability of having a particle that started at, where have it started? Starting at X and being at Y at time T. So you had the stochastic differential equation driving particles, but you can look at their density. This is now a probability density. So we went from particles in high dimensions to unknowns that now are infinite dimensional, the probability density. So it seems like we're worse off. But PT satisfies a linear equation of diffusion type. It's a Fokker-Planck equation. So the derivative of P with respect to T, it has a Laplacian term that comes from the noise and a drift term that comes from the drift term of the SD. And so we call HFP the generator of this PDE. And this is all classical stuff. And under very general assumptions, there are eigenvalues and eigenvectors for HFP that accumulate all the plus infinity. HFP is not self-adjoint, but it's almost. If you change the measure, it's conjugate to a self-adjoint operator, and so it has eigenvectors. And so model this transformation, there is a unique set of orthonormal eigenvectors. If you don't do this measure transformation, then you're going to get right and left eigenvectors, which I call phi and psi. And so you can expand the solution, PTXY, onto this basis of eigenvectors. There is going to be an eigenvector phi naught corresponding to the eigenvalue 1. Phi naught represents the stationary distribution. If you let t go into infinity, you're going to get phi naught. And when t is finite, you're going to get a sum of infinitely many terms in terms of those eigenfunctions. And that are decaying with rate that depends on the eigenvalues of HFP. Now, okay, so there is this PD, but it doesn't seem very helpful because we need infinitely many terms. But of course, since there is that exponential decay factor, we might hope to be able to truncate the plus infinity to some small number, small d, which is where we would like to operate. Okay, on the other hand, we don't know HFP, so we don't know the eigenvectors, we don't know the eigenvalues. We're only given data from trajectories. And so the new and important step here is the following. Given just data from trajectories, we would like to construct estimators for HFP, phi j, psi j's, and lambda j's. And that's, so all of this has been joint work with many people throughout the years, Rafi Koopman, Stefan Lafont, Yanis Gavrakidis, Boaz Nadler, and several others. So how do we get from trajectories estimators for these eigenvalues and eigenvectors? We do a construction which is very general in machine learning. It's tied to manifold learning and dimension reduction in that field. And it's a construction that starts with xi's, our samples of trajectories of molecular dynamics. But in fact, xi's could be images, text documents, they could be just data points, pieces of time window, pieces of time series. And we define a similarity function that decreases with the distance between points. So maybe the canonical choice is e to the minus distance between 2 points squared divided by some constant sigma. Notice that the point of the similarity is that it's very close to 1 when points are closer than, say, square root of sigma, and it's very close to 0 when points are farther than, say, 4 square root of sigma. So it's a local similarity function. And out of this local similarity function, one can construct a weighted graph where the vertices are the data points, in our case, configurations of a molecule. And these data points are connected with edges with strength given by W. And so two molecular configurations which are very similar, according to the similarity function, are going to be connected by a strong edge in this graph. And now, once the graph is constructed, everything that is being done on the graph is completely intrinsic in the sense that if these molecular configurations lie on or close to a low-dimensional manifold, this graph is modeling that manifold, and the ambient dimension, the large dimensional spaces completely disappear. The most canonical thing you can do on a graph is taking a random walk. So a random walk is a process on the graph where you jump from vertex to vertex with probability proportional to similarity, or if you want the weight on the edge connecting the 2 points. And so W is a n by n matrix of similarities between each one of the n states, each pair of n states. And you just normalize that suitably, so you get a matrix representing the random walk, P, and Pij is the probability of jumping from xi to xj. This random walk is not quite symmetric as an operator because we normalize by the inverse in front of W. W was symmetric, but P is not anymore. But P is conjugate to a symmetric operator. It has nice real eigenvalues and eigenvectors. I'm going to call the eigenvalues lambda I, the eigenvectors phi i's. And one can use the eigenvectors to embed the graph in low dimensions by mapping every vertex of the graph to the value of the first m eigenvectors at that point. Each eigenvector is an n vector, so you can think of it as a function of the graph. In fact, it's a generalization of Fourier modes on that graph. And this map takes the graph and it sends it to Rm, where m is the number of eigenvectors that you're going to use for the mapping. What's the relationship with what we were talking about before? Well, up to minor modifications that I'm not going to go into, modifications in the definition of W, if the xi's come from a Langevin equation of the type that we described with a minus gradient of u plus noise, then a suitable choice of W has the following effect. As you collect more and more points, so as n goes to infinity, the random walk that we're constructing here converges in a suitable weak sense to the generator of the Fokker-Planck equation that we talked about. And so the eigenvalues and the eigenvectors converge to the eigenvalues and eigenvectors that we wanted in order to approximate solutions of the Fokker-Planck equation. And so only given data and the knowledge that the data were coming from a process of a certain type, a Langevin equation of that in that form, we can construct eigenvalues and eigenvectors of the generator of the Fokker-Planck equation. All right, so here are some examples. So the first one is a very small molecule, an ND peptide. First of all, we want to check if the trajectories of this molecule in about 30 dimensions are intrinsically low dimensional or not. Well, we can pick a point. Here I'm representing that point in the reduced state space, but of course, corresponding to this point, there are, 30 minus 2, there is a submanifold dimension 30 minus 2 states. I pick one of those, and I can look around that point and ask whether the trajectories are close to being low dimensional. And I can do that by using multiscale PCA. And above is a plot of multiscale PCA. So the x-axis is distance from a configuration here, and in the vertical axis are the singular values of the covariance, local covariance matrix. And we see that there is one or maybe two large singular values, and all the others are much smaller. So near that mountain pass, trajectories are 1 or 2 dimensional. If I go near the bottom of the metastable state, one of those lakes there where the free energy is small, and I do the same operation, then as a function of the distance from that point, then my singular values look very different from the top. Here I would say the dimension intrinsic dimension is maybe 2, maybe 5, maybe 8, still much smaller than 30, but definitely different from how it looks at the mountain pass. And so this makes me think of the variables that Simon was talking about this morning. All right, they arise very naturally. And there are physical interpretations of why the situation is like this. But the point is that the intrinsic dimension is smaller and sometimes much, much smaller than the dimension of the ambient space. All right, let me not say that. And so if the intrinsic dimension is small, it makes sense to do these graph constructions and trying to use a very small number of eigenvectors in order to approximate the solutions of the Fokker-Planck equation. And so we run long simulations of a molecule, we connect the states in the way that I described, we get a random walk, we compute the eigenvalues and eigenvectors, and then we use our eigenvectors instead of the two angles phi and psi suggested by the physical chemist. And so this is our first diffusion coordinate, that's the second diffusion coordinate, and this is a free energy computed in the diffusion coordinates. And we see that the first diffusion coordinates separates one metastable state. This was the metastable state at the bottom in the picture before, from the at the top, from the other metastable state, the alpha one, which was over there. Oh no, alpha, yes, at the bottom, and the other one at the top. So it's just sort of like that, rotated. So the first diffusion coordinate separates the two main metastable states, and then actually the second diffusion coordinate separates, so this metastable state actually had two sub-metastable states, which were weakly connected, and that transition is being parameterized by the second diffusion coordinate. And there are gaps in the eigenvalues, which suggests that two diffusion coordinates should suffice. And then what we can do is we can also project in just one dimension the first diffusion coordinate. This is the free energy in that one diffusion coordinate, one metastable state, another one, and an energy barrier. And we can ask if we can write a Langevin equation in one dimension such that the expected transition time to go from here to here, one metastable state to another, and back, is close to the expected transition time in the original 30-dimensional space. And the answer is yes, we can construct a Langevin equation just in 1D with this free energy surface, which has the correct rates. All right, so this reduced model is faithful only in the sense that transition rates here are close to the transition rates in the original system. Transition rates, of course, are large time phenomena. We're not approximating single trajectories by any means. We have discarded so much information here. We're down to one dimension, but there is still a Markovian system here with the correct transition rates. Now, this is a teeny molecule where everybody with a new algorithm tries his hand to see if things work. We've done more complicated systems. This was a system with about 300 atoms, so the dimension starts to be around 1,000. It was reduced to about 300 with some things that I'm not going to describe. But the molecule has a folded state and a very large unfolded state. And when we compute diffusion coordinates, we immediately parameterize the transition between folded and unfolded. And we can also go and check the intrinsic dimension. And the intrinsic dimension here is crazy. It can be, you know, up to maybe 20 or even maybe 30 in this regional state space, 30 out of 300. But then it collapses along the transition to the between folded and unfolded. So these blue regions over here correspond to very small intrinsic dimensions. So again, a very complicated varifold occurring here. And we also applied the same techniques to systems where people had tried to come up with reduced coordinates and they failed. So all the reduced coordinates that had been tried led to one-dimensional systems that were not Markovian. And so you couldn't even talk about rates of transitions. And so we ran our algorithm. We get a one-dimensional parameterization. And the system looks Markovian in one coordinate, and we get good approximation of the transition rates. And so I'm like, OK, we're done. And my colleagues in chemistry, of course, are like, we haven't learned anything. We don't know what the coordinate is. Right. So how do we do that? So I asked them to write down a list of all the physical observables that they understand about this molecule. And then we checked which of those are a one-to-one function in one-to-one correspondence with the coordinate that the machine learning algorithm has found. And this coordinate was almost exactly one-to-one with one of those physical observables, and that was the explanation. And after the fact, they said, oh, of course this was a good coordinate. I mean, I could go into the physics of the example, but I was glad that the explanation that we found a posteriori actually made a lot of sense to them. Eventually, it made sense to me, too. So this was all about the situation where we have this high-dimensional system. We can afford running long simulations. And from all this high-dimensional data, which we do a model reduction that preserves rates between metastable states. Since I still have 10 minutes. No?
Actually, it wasn't.
Oh, I don't? Oh, I have 2 minutes. All right, because I started 10 before. All right. Yes, so I'm not going to tell you almost anything about the second part, except that you know, we got greedy. We said, well, sometimes it's really expensive to collect these long trajectories. Can we do without collecting the long trajectories? And so just at the very high level, this is a different problem where we have our complex simulator for molecular dynamics. And now we are not going to allow ourselves to run the simulator for very, very large time. We only allow ourselves to run it many times, but each time for a very short time. So we are able to collect, we allow ourselves only to collect a lot of short paths. The idea is that if you have many computers, each of them is going to run one of those short paths. It's easy to parallelize over short paths. It's very hard to parallelize one long path, of course. And we want the output of our construction, given a lot of short paths, carefully chosen, initialized, with initial conditions carefully chosen by our algorithm, we are going to output not a reduced model, but another simulator. So we output a simulator, we output a system of stochastic differential equations in the same dimension as the original state space, but this simulator has only 2 gears, and it runs much, much faster than the original one. And even if it was constructed only from local in time and space information, only from short paths, we can prove that if you run this simulator for a very large time and you look at the stationary distribution of the simulator, the stationary distribution is close to the stationary distribution of the original one. So even if it's constructed from local information, it has large time accuracy. And I'm not going to say almost anything here, maybe just one simple example. So this is a stochastic system in 12,000 dimensions. It's my favorite white circle jiggling around and moving around. And all the algorithm is given is a parameter, delta equal to 0.2, which tells to the algorithm that you shouldn't care about any detail of the system below that time scale. Okay, so small time doesn't matter. Try to compress the system above that time scale. The system initializes trajectories. This is one such trajectory in about 12,000 dimensions. And it produces a simulator in 12,000 dimensions, which is accurate for all times. The theorem says that we are accurate here at very large times. It's easy to show that we're accurate here, but we're in fact accurate for all times. This is the difference between running the original system and looking at the distribution of paths, that's pt x dot, and running our compressed simulator with the same initial condition x, that's p hat t, and we look at the total variation distance. And moreover, there are many metastable states in this system. There are 3 of them. And in blue are the expected times it takes to go from one metastable state to another by running the original simulator. And in red, it's what we get with our simulator. So we not only preserve the stationary distribution, which is this number here being below delta, but we also preserve transition rates. All right, so I'm going to stop here since I have -3 minutes. Yeah. All right.
Excellent. Other questions?
Okay, I have
Yes,
a bunch
Javier.
of questions.
All right.
I'll be given only one.
All right. Just the hardest one.
Okay, so I'll start from there. So you have the molecular dynamics equations.
Yes.
It is essentially a Hamiltonian system plus Brownian motion, and it is essentially a quasi-integrable Hamiltonian system because you have van der Waals forces.
Yes.
And you translate it to Fokker-Planck, and then in Fokker-Planck you project it on a finite dimensional subspace spanned by eigenfunctions.
Right. Yes. Mm-hmm.
The question is, what happens to Hamiltonicity? Because we know that if you have a Hamiltonian system,
Yes. Mm-hmm.
and you solve it with a symplectic method,
Yes.
then you,
Right.
you conserve quantities
Yes.
and precision for a very long time.
Absolutely. Yes.
Now, suppose you take it to Fokker-Planck,
Mm-hmm.
okay, suppose you translate it back to ODE formalism.
Uh-huh.
Is it still Hamiltonian plus Brownian motion?
So our reduced model is not. I mean, it's not. We've thrown away so many coordinates. We don't conserve any of the Hamiltonian structure. But we are also asking a question that doesn't necessarily require the preservation of the Hamiltonian structure, because the question that we're interested in is, are the transition rates between metastable states in the reduced system close to the ones of the original one? Well, is the stationary distribution, and are the transition rates preserved? And for that, I believe you don't need to preserve the Hamiltonian structure.
You don't need, but it immensely helps. Because
But of course, right, so it would help, but I don't know how to preserve it. And you know, when, you know, the only alternative that I know is to run the original system with the technique, say the method that preserves the Hamiltonian structure, and then I have to run it for a very long time. And so we're walking a very strange path here. I mean, we are butchering the physics to a high degree, but we are also doing it in a very specific way, which is all about preserving stationary distribution and transition rates. And so I don't think one needs to preserve the Hamiltonian structure for doing that.
Are there other questions? One more short question.
okay, another one. You mentioned inertial manifolds right at the beginning.
Yeah.
Now, the problem with inertial manifolds is that you need to know the right dimension.
Yes.
If you get it too small, it becomes useless.
Right. Yes.
If you get it
That's
too
true.
large, then you have redundant dimensions that add
Yes.
to your
Mhm.
work. And the answer is that almost nobody knows what are the inertial manifold dimensions. There are
Fantastic.
almost no theoretical results.
Yeah, that's a great question. So, and I don't have a theoretical result either. Typically, I'm very happy to overshoot because so I didn't have time to go into any of the results, but in all of the theorems, we have a complexity, both in terms of number of samples and computational complexity, that scales linearly or at most quadratically with the intrinsic dimension. What does that mean? It means that, I don't believe any precise dimension here, right? These are all approximate intrinsic dimensions. Looks like 5. Let's make it, 15. I don't pay 2 to the 15 versus 2 to the 5. I pay 3 times as much to use 15 dimensions instead of 5. And this is even in this second part of a talk where we construct this reduced simulator. We have to estimate drifts and diffusion coefficients and so on. It seems like, if you work in 15 dimensions instead of 5, you'll be completely lost. In fact, we can prove that we only pay quadratically in the intrinsic dimension. And so my ad hoc answer, again, it's backed partly by theory, but it says you don't have to guess the correct dimension, and you pay very little for being very conservative and estimating a much higher intrinsic dimension. I would love to be able to, be more precise, but I'm not even sure what the correct definition of dimension is here, right? These are all trade-offs. The dimension is not 3, is not 5. It's, if you choose a 5-dimensional thing, this is how much higher you do. And so this trade-off is something that I would like to understand better. But right now in practice, I'm always overshooting what I think is the dimension that I need for my accuracy.
Thank you. Thanks again.